Okay, let's go. All right, last two problems, last two sections here. So 8.3 is so we're going to test things that are dependent now. So that means it's one of two things here. One is that people are matched up with each other, or more commonly, it's the same person being tested twice. So we call them dependent samples. All right, let's go with the formula for it, and then we'll jump to the problem here. So testing the difference between sample means and its dependent samples. All right, let's go with it. So first things first is jump to, and tell me if I'm going too fast. I can jump back to it here, but here's a few little things we got to keep in mind. They're different. Not too bad, not too bad here. So first things first, we are going to have to tabulate by hand the difference. There it is. It's called a t-statistic. Then we're going to have to tabulate the standard t-statistic here. And so a few things happening here. There's almost like different programs. Sorry, different equations that we have to put into. So all these are different pieces. We eventually have to write it into one. All right, and this one's by a little bit of a longer process, but we're only going to use, let's see, looks like eight. Yeah, It's almost easier to do it individually and then put it together at the end. Yeah, individually. Okay, so let's see. First things first, we should notice this is a English letter S, the D next to it. So that means this is a standard deviation. And if you guys think back all the way to chapter 2, do you guys remember doing the standard deviation in chapter 2? We made a table of it, some other stuff here. So this is totally going back to what we did. And let's go for it here. So here's what that we have a manufacturer. There it is. We got a shoe manufacturer. Here it is. Claims that athletes can increase their vertical jump after training in their shoes for a while. This is the example, and we'll just kind of don't need to write down all of it. Let's on the next slide is actually going to give me the so don't write it down yet. How about that? We'll just kind of do it. So shoe manufacturers, just kind of read it here. So increase the vertical jump in heights. The vertical jump heights, they select 8 randomly selected athletes. And notice what happens is they use the shoes for 8 months and they test again the vertical jump. Cool. Okay. In inches, alpha level is 0.10. And notice here, athlete 1, old one was 24, new one was 26. Old one was 22, now it's 25. Are we good? So now the question is there a difference in height? And interestingly enough, this is where things get complicated here. So is it because they trained a lot more, right? Or is it just because they just chose shoes? Yeah, so there's a causation issue that happens here. All right, so what do? Here it is. We set up a, oh, sorry, I'm going a little too fast. So first things first is the way we're going to measure the D value is this going to be the jump before the shoes and the jump after the shoes. So somehow you got to make an equation for D. Like, how are you going to calculate the difference? And in this case, jump before the shoes, it should be shorter, right? Jump after the shoe should be higher. So if you get it to the negative values, that actually is a good thing, right, for the shoe manufacturer. Okay, I guess we should do this one too here. Let's see. Can we do the claim as well here? So HO and HA. Let's do that as well. So again, slightly different one. And I'm not sure why they didn't give us the 3 different possibilities here. So here's what we got. The mu difference is going to be greater than or equal to 0. And the average difference is less than 0. All right, and this one looks to be our claim. Okay, next. If that's the case, I'm thinking something looks like this. Is that right? Got that? And looks like we're looking at this to be the alternative area. That to be the lower better. Next is, let's see, alpha level 1.01. It's a one-tailed test. And our D, degrees of freedom. Let's say we have 8 athletes here. Therefore, degrees of freedom is 7. So according to your chart, give me degrees of 7 and the T value if it's a one-tailed. I got a negative 1.415. Are we good with that? I'm gonna write it in, see if you guys are okay with this one. Negative 1.415. So notice degrees of freedom is 7. So we'll cross there. The rejection region should be that right there. I don't have a sheet in front of me, so you guys have to verify. Is that true? And we're on the t-test, right? Yep. Yep, perfect. So t-test, one tail, and we were at alpha level of 0.10. Okay, perfect. Right. Okay, we got that. And now let's calculate our t value. So this one's gonna be a little different. This one we gotta do by table. We're trying to figure out the difference between each individual piece. Good. That's what we're looking at. So it looks like this. So you got the before and you got the after. It is a big table. Good. And if you want to do maybe just like the first 2, right, and put ... that's fine as well. And put the very bottom. Let me put all the formulas in here though. So all the formulas, not to scare you guys too fast here. So it's a table. Here's your before, here's your after. So 24 minus 26 would be a -2. Right, so minus means better, right? And then what we're going to do is we're going to square it. Square each of these terms. Add up the differences. Difference is -14, so overall 8 players with the overall difference of -14 inches. The square of it becomes 56. And you got these formulas here. We're going to do it by parts. So we call distance bar, or the average distance of the sample, is all the differences added up, divide by how many players there were in the first place. So on average, each player gained what, 1 and 7, almost 2 inches, I guess, right? For average. That's what that one is. All right, then we got the next one to deal with here. So next one, formula looks like this. It's the additions of all the distance squares minus the -14 squared over how many players there were, and all that divided by 7. So can you guys punch that in? Simplify it first, I guess, if you can, and then punch into calculator. See if you guys get a 2.1213. All right, remember all these numbers are just to get us to our standard sample test statistic here. Okay, and then tell me when you guys are done. We'll punch it into the final formula here. If you know the final formula already, go for it. All right, we good? Those still copying? Almost done. One more calculation, we're done. All right, what this happens in real stats is that usually we put this into an Excel spreadsheet, and then you're doing more like those kind of computations, not doing it by hand. All right, are we good to go? Next one? Okay, so we got that all done. Let's go with it here. We're gonna punch into this little guy now. And done. As you guys are writing that down, let me show you the rest here as we go. So then we have alpha level. There it is, rejection region. Our cutoff point was a negative 1.415. We put a little dot at negative 2.333. That's actually pretty good. That's anything above 2 or below 2, that's pretty good. So we get to reject the null hypothesis. And remember, is our claim the null hypothesis or the alternative hypothesis? Okay, we're good there. Tell me if you guys. So we reject the null hypothesis. I think the claim was the alternative hypothesis, right? Manufacturer's shoe claim was it is actually going to increase the vertical jump of the players. So in this case, yes, there is enough evidence at the 10% level to support the shoe manufacturer's claim. That means on commercials, you'll see it has been proven. Right? You'll see all that kind of stuff in advertising. It has been proven that this will guarantee an increase in your vertical jump by these shoes. Now, anybody seen like that advertisement like that for like baseball equipment or anything else like that? Like, hey, this is going to improve your swing or this will improve this. Just try this. It's been proven that this will increase this. Okay, that's true. Yeah, exercises or something like that. Yeah, that makes sense. Yeah. Okay, so let's go. All right. Okay, are we good there? Okay, one last problem, and one last concept here. You guys did a good job here. So 8.4, here it is. The only thing is we're going to change our direction and we're going to look at proportions. And proportions just means percents, right? Testing difference between percentages. Let me give you the formula and we'll do one example. It's 8.4, one last equation and one last problem. Let's go. So let me give you the equation. So for proportions, it looks like this. Oh boy. So if you guys can write this one down, it's this guy right here. So instead of mu, now it is P, right? Because P stands for proportions, mu is for means. So we have that equation, not too bad. I think 8.2 was the worst with, yeah, I'm just going to give you one quick condition for it. Okay? So there's your equation Z. We're back to Z-score. So it is the probability hats of each one minus the probability of each one over maybe we have a P bar now. P bar. If you guys remember using these for proportions for chapter 6 and chapter 7, remember how they had to be at least 5, right? That's what gives you. So we'll write a little condition here. It's there, almost there. That's that big standardized test statistics, and then when P bar is that and Q bar is that. Okay, now I got to give you guys the condition here. So we got to test the conditions. If you guys remember back from chapter 6 and chapter 7, these are the conditions if we can use this in the first place. So just right here, just these little pieces right here. So the number that you use and the percentage that you use, they have to be 5 or bigger. So that's the condition. And if you can use that, that means you can use the Z-score. Approximate. That's so we got to check that first to see if it qualifies, and if it can, then we can use it. So this is the condition to use the formula. All right, we're good now. Let's go with this. So this is the condition we can use it. So let's use it. So last problem of the chapter, here it is. So let's do a medical research here. We're doing medical research to see the study of the effect of a cholesterol reducing medication. So at the end of the study, the researchers found that out of the 4,700 randomly selected subjects who took the medication, 301 died of heart disease. Of the 4,300 randomly selected subjects who took a placebo, only 357 died. So now the question is this. Well, actually 357 died. So now the question is the difference between 301 and 357, is that significant enough? That's the question. So just like, because this is a medical, usually in medicine, we go to a 0.01 alpha level. And then whatever's in the box. So key. Yeah, just one more problem, guys. There it is. So how do we find this? We take the 301, we divide it by 4,700, and we get this little value right here. That's where this comes from. That's just x1 divided by n1. We good? About 6%. Okay, then we go over here. We do x2 divided by n2, and we get ourselves 8%. So now the difference between 6% and 8%, is that significant enough? All right, so we got our p hat 1, p hat 2. All right, we're good. Let's go with it here. So first things first, we have to get our P bar and our Q bar. So here's this right here. So our P bar, so both of them added together, what's going to be like the average between both of them? That's kind of what we're. So we add the deaths together, we add the total number together. And once you do that, you subtract from 1. And you're going to get your other percentage, the contrary percentage here. You do have to test them to see if they're bigger than 5 at this point. And yes, they all are. I'm going to just write it in here. So you can just write bigger than 5. So we have to write each of them, but you have to test each one of those. It's getting to the end of class here, so I'm going to kind of give you the piece of the problem. We're good. And I'll give you the answer, and then we'll come back to the big equation that you got to fill in, those that want to fill it in. So 301 plus 357 divided by the total number of participants in the study gets you 7%-ish. The opposite is about 93 or 92%. Cool, almost there, almost there. So let's go with what we have here. So we have the claim, right? The claim is that this drug is going to lessen the number of the percentage of people that die from heart disease. The exact opposite view would be that this drug actually increases it or is the same. So this has to be a left-handed test. If you have an alpha level of 0.01, that means your rejection region starts at negative 2.33 and a positive 2.33. I'm sorry. It's a left tail test only, right? So the rejection region is only on the left side. Both on the right. So negative 2.33 is the start of the rejection region if you want to draw it out. So we have this, right? It lessens the number, and Z not the negative value of it. It's going to be a negative 2.33. Okay, so we got that. Here's the big computation for it. There it is. It is on top. Notice we're going to do the same thing. We're going to reject, forget the zero that's in the middle, right? That's a zero. Make sure you have this in parentheses here. Make sure you guys have that in parentheses right there. And the bottom, again, it's a whole big entire square root. So no need for parentheses there. This big old square root there. All right, and try this on your calculator. So you can put it in. So forget the zero at the end, put in parentheses, the stuff in the numerator. All right, and see if you guys can get that on the calculator. All right, I'm gonna let you guys try it, but I'll come by, see if you guys can do it here. Let me give you guys the answers and then we'll come back to this. We'll come back to this slide again. So I got a negative 3.46. So let's see what happens here. And negative 3.46, if I are to graph it, it does go into the rejection region. That's true. And so we reject the null hypothesis. And our claim was alternative hypothesis. True, true. Therefore, we have enough evidence at the 1% level of significance to support the claim. And the claim is this drug does lessen the amount of the number of people that die due to heart disease. There it is. Whew. That is it, class. That is the end of chapter 8. Right.